Okay, so let's go over quickly some of the things we covered last time. So last time we introduced Lie algebras. So there's a Lie algebra is a vector space with a bilinear operation satisfying skew symmetry and the Jacobi identity. And we saw that we explained a procedure about how to assign a Lie algebra, a finite dimensional Lie algebra, to any linear algebraic group. So first of all, there's a procedure that starts with any associative algebra, and you can think of it as a Lie algebra just by taking the commutator of elements in the original algebra. And many Lie algebras appear as sub-Lie algebras of a Lie algebra coming from an associative algebra. So for example, we saw the associative algebra of endomorphisms of a vector space. And if V is finite dimensional, I guess, then we can think about the traceless endomorphisms. And that's a Lie subalgebra. That's not an associative subalgebra. And similarly, if we had the derivations of R algebra, those form a Lie subalgebra of all R linear endomorphisms of the algebra. And if we have a group action, then the endomorphisms that commute with the group action, those also form a Lie subalgebra of the endomorphism algebra. So we saw all those examples. Yeah, so the invariant an endomorphism is you can think of it as an invariant under the group action, which means it's equivariant as an endomorphism. And the space of those form a Lie subalgebra, and similarly for derivations. We had the notion of a morphism of Lie algebra, so it respects the bracket. And a representation of a Lie algebra is a morphism of Lie algebra from G to GLV for some vector space V. So GV is just the endomorphisms of V thought of as a Lie algebra. And we saw, we defined vector fields on an affine variety as derivations of the affine algebra of X, and these form a Lie algebra. And we saw that if we have a group, a linear algebraic group acting on an affine variety X, then there's a notion of a G equivariant vector field. So these are the vector fields that commute with the action of G on the affine algebra. And we had the example of GM acting on I guess it should be K, and we computed what the equivariant vector fields are in that case. And then we had this result that if we have a linear algebraic group and an affine G variety, then an equivariant vector field is so for every orbit, it's determined by 1 point on the orbit. So if we know what the value of this equivariant vector field on 1 point little x, then we know it on all gx, because we can use the translation action. We can use the action of the group to get the value of the vector field at all the other points. And yeah, it's if and only if. So if we have this property, then the vector field is equivariant. And the equivariant vector fields form a Lie subalgebra of all vector fields, and it's often much smaller. And if we happen to have a torsor for G, so a principal homogeneous space where G acts transitively with no stabilizers, then the equivariant vector fields are just determined by their value at 1 point, at any point in the space. Yeah, so we have an isomorphism of vector spaces. Okay, so yeah, so we have the proof of this. And yeah, and then we focused our attention on G, the linear algebraic group, as a principal homogeneous space for itself under the left translation action and the right translation action. So we have these two actions on G, they commute, and we have the notion of left invariant vector fields and right invariant vector fields. And we proved that those, as Lie algebras, those are isomorphic Lie algebras. So we can pass from left equivariant to right equivariant by conjugating by the antipode. The antipode is the order 2 algebra anti-automorphism of the affine algebra of G. So we have that, and then I presented a different way to think about this Lie algebra. So if we had the coproduct map on the affine algebra, and the coproduct map gives the affine algebra the structure of a coalgebra, and the dual of the affine algebra, so just all linear functionals on the affine algebra, has an associative algebra structure just by taking duals, precomposing by the coproduct map on the affine algebra, so derivations. So the tangent space of the identity at G are derivations from the affine algebra to the field thought of as a module for the affine algebra via the evaluation at 1 map. And so in particular, these things are linear functionals on the affine algebra of G. So they belong to this dual space. And the claim was that this is a Lie subalgebra of this dual space. So this dual space is an algebra, in particular it's a Lie subalgebra. We can ask for something to be Lie subalgebra. And so I showed the proof here, introducing Sweedler notation. Hopefully you got a chance to get familiar with Sweedler notation. And so because of this, we get a Lie algebra structure on the tangent space at the identity. So I'll think of the Lie algebra of G as the tangent space of the identity equipped with this Lie algebra structure, but it's isomorphic to the other one. So if we just evaluate any left equivariant vector field at the identity, we get something in the tangent space at the identity, and this map is the isomorphism of Lie algebras. So we can go back and forth between these manifestations of the Lie algebra. So this is kind of the summary diagram. We can think about left equivariant vector fields, right equivariant vector fields, or the tangent space at the identity, and these are all the same Lie algebra. We have these isomorphisms. Okay, and this is kind of abstract. So to think about the Lie algebras in specific cases more concretely, we need to do a little bit more work to analyze what happens in the GLN case. So as we argued, so first of all, in the GLN case, it's enough to compute the tangent space at the identity for n by n matrices. And we argued that the affine algebra of n by n matrices is also is a coalgebra, so its dual is an algebra, and the tangent space at the identity is a Lie subalgebra. So that was for matrices, and the claim was that there's a map from n by n matrices to the dual of the affine algebra of n by n matrices. And it's given by the following thing. So if we can define this map based on where the elementary matrices go. So an elementary matrix Eij goes to this linear functional, which is a derivation from which is in fact a derivation where we first take the partial derivative with respect to Tij and then evaluate at the identity matrix. And we argued that this is an injective algebra homomorphism, and its image is exactly the derivations from the affine algebra that are valued in K1, this module given by the evaluation at the identity map. So in this case, the tangent space at the identity is actually an algebra, more than just a Lie algebra. but that's something very special in this case. And yeah, and in general, we'll have for a general linear algebraic group, it'll embed into some GLN, and its Lie algebra will be a Lie subalgebra of the Lie algebra of GLN. So the specific Lie algebra it is depends on which group it is, but this is a general procedure for figuring out which Lie algebra we have. So at this point, I want to switch to the next PDF. So this is the clarifications for Lie algebras that should be on the website. So yeah, so there was the question of how do we see that in the case of SLN we get traceless matrices? That's a very good question, and I feel like I didn't really explain it that well last time, so I wanted to elaborate on that point this time. So first of all, just like I said before, we have this isomorphism of Lie algebras, tangent space at identity, and by n matrices, where this the elementary matrix Eij corresponds to this partial derivative composed with the valuation at the identity matrix. So that's what we had from last time. And so now the claim is that under this isomorphism, the Lie subalgebra of SLN, so that is a subalgebra here, that's identified with the Lie subalgebra of traceless matrices on this side. So that's the claim. So how do we see this? Well, let me give you the kind of the sketch of the main points of the proof of this claim, and then there'll be some details for you to fill in if you're interested. So first of all, we take the determinant map. So this is a polynomial in the Tij's. It's some polynomial, and we know that the affine algebra of GLN is the localization of this polynomial algebra on the Tij's at the determinant element. And we also know that the affine algebra of SLN is the quotient of the affine algebra of GLN by the ideal generated by the determinant -1. Or equivalently, we could just start with the polynomial algebra and then quotient out by this ideal.
Why is it localization just? Why just the localization by determinant?
For GLN, you mean?
Yes.
Yeah, so because GLN is defined as the invertible n by n matrices, and a matrix is invertible if and only if its determinant is non-zero. And we had this stuff from the algebraic geometry section that to define the space where a function is non-zero, the functions on the locus where that function is non-zero is just a localization. Okay, so we had that. And so now there's a bit of work to do, and that's to argue that if we take this determinant element, we think of it as some polynomial, and we apply this partial derivative and then evaluate at the identity n by n matrix, then we get 1. So then we have to get some scalar, something in the field, right? Because this evaluation lands in the field. And we get 1 if I is equal to j and 0 otherwise. And a hint to get you started is you can use this recursive definition of the determinant polynomial. So so in general, this is coming from the fact that the one way to define the determinant of an n by n matrix is in terms of determinants of n minus 1 by n minus 1 matrices. And the formula is the following. So this is the first row expansion. You can do the first column expansion or any row expansion or any column expansion, but the first row expansion will be this formula. So we have Tn, so the n by n determinant is given as a sum T1L times plus or minus 1 determinant of the matrix formed by deleting the first row and the nth column. So if you start with this and you apply this partial derivative and evaluation of the identity, you can verify by induction that this claim is true. So that's the work here. And once we have that, then we're pretty much done. So now if we take something in the tangent space at the identity of GLN, then it's a derivation from affine algebra GLN to K1. And we know that it's given by, it's a linear combination of these xi ij's from before. These form a basis for this vector space. And so it factors through, so this defines an element in the tangent space of the identity of SLN, if and only it factors through the affine algebra of SLN as a derivation from GLN to K1, because there's a quotient map from affine algebra of GLN to affine algebra of SLN. Okay, and so that happens if and only if the kernel of that quotient map is killed by xi, that kernel is generated by det minus 1. So we just need to verify that xi of det minus 1 is 0. That happens if and only if, so this is just the expansion of xi in terms of the xi's. This is just applying the definition of the xij's. And then if we do the partial derivative with respect to a constant, that disappears. If we do this partial derivative composed with eta of det, then we already saw that that's 1 if I and j are equal and 0 otherwise. So that's how we get this this sum here of the ai's. And so then xi under the isomorphism from at the top, xi is corresponds to the traceless matrix. So that does it. Yeah, any questions about this computation? Okay, yeah, maybe it's a bit confusing if this is the first time you see it, but it's pretty straightforward. Right, so in particular, SL2 is traceless 2x2 matrices. So we can write, it's three-dimensional, and we can write a basis for this vector space in terms of the following matrices. So any traceless matrix is a linear combination of these three matrices in a unique way. And if we want to compute what the bracket is, so we just compute the bracket of these generators. So this will be commutative matrices, and you can check that the bracket of H and E is 2E, the bracket of H and F is minus 2F, the bracket of E and F is H. So these are the fundamental SO2 relations. And yeah, so then GL2 is kind of similar, except now we don't have the trace equals 0 condition. So we have what I'll call H plus and H minus. So any 2x2 matrix is a linear combination of these four matrices, these form a basis. And the relations are as follows. So H plus or minus E is plus or minus E. H plus or minus bracket with F is minus plus F. The H is commute. And if we take the bracket of E and F, then we get H plus minus H minus. So that's for GO2. And one more example. So we saw that, so in the TA session, you guys computed that that the tangent space of the identity, I guess, of O3 is this, but SO3 is the connected component of the identity of O3, so we can just restrict our attention to SO3. And so the tangent space at the identity can be identified with skew symmetric 3x3 matrices. So in other words, matrices for which M plus M transpose is equal to 0. And so if we want to come up with a basis for this space, then it's pretty easy to see that anything in any such matrix will have zeros along the diagonal and will be skew symmetric when we flip. So then anything is a linear combination of these three matrices. So we have 1 and minus 1 here, 1 and minus 1 here, and 1 and minus 1 here. Right, and then if you, what are the relations in this case? So there's this sort of cyclicity here. So B bracket A is C, A bracket C is B, C bracket B is A. So you can check this. And so this looks like kind of, this looks interesting. It looks like an ostensibly different three-dimensional Lie algebra to SL2, but in fact there's an isomorphism. So this is one of those coincidences in low dimensions. There's an isomorphism between the Lie algebra of SL2 and the Lie algebra SO3, and it's given by this, I believe. I may have gotten some signs off, but this is the idea. Right, so those are some examples of Lie algebras. Yeah, okay, those are the clarifications I wanted to make. Any questions on this before we move on to discussing the adjoint action? All right, then let's move on. All right, here we go. So, all right, so the next topic to talk about is the adjoint action. Okay, so what is it? So let's start with the linear algebraic group G. We have the Lie algebra, which we realize is the tangent space to the identity. And again, the bracket is coming from this associative algebra structure on the dual space of the affine algebra. And the adjoint action of the group G on the Lie algebra G, frac G, is defined as follows. So if we take, so little g in the group acts on tangent vector xi in the following way. So we differentiate this map CG, which is the conjugation by G map, and we apply xi. So this conjugation by G map takes the identity to the identity. And so its differential at the identity is just an endomorphism of the tangent space at the identity. And that's the endomorphism by which little g acts in the adjoint action. So, and by definition, differentiating a map amounts to precomposition with the associated pullback homomorphism on algebra homomorphism. So we have CG, we have its induced map from affine algebra of G to itself, and we just precompose that and then apply xi. That's what this action is doing. So this is the adjoint action. And this is an action of G on a vector space. So the Lie algebra is just a vector space. It's a finite dimensional vector space. So, and this is a linear action. So you can check that this is linear. That's just because each one of these endomorphisms of the tangent space at the identity is a linear map. So it's a representation of G on the Lie algebra. Okay, so that's one way to think about the adjoint action. There's another way to think about it in terms of left and right equivariant vector fields. So if we take, so we have the following representation. So if we take a left equivariant vector field or left invariant vector field, then G can act by it by conjugating by the action on the affine algebra coming from right translations. So remember the rows, we had these rows and lambdas. These were coming from the right and left translation actions respectively. And there were algebra endomorphisms of the affine algebra of G, so K brackets G, and they commute. And because they commute, this is a well-defined action. So if we have theta and we conjugate it by this rho g, then that's still left invariant because these rhos and lambdas commute. Similarly, if we started with something that's right invariant, then we can conjugate it by lambda g, and then we obtain something that's again right invariant. That part doesn't change. So we kind of play these two actions off of each other. So the claim is the following. So first of all, the adjoint action and each of these actions defined here on left and right invariant vector fields, they're compatible with the Lie bracket. So every element in the group acts by Lie algebra automorphism. So the action of the group respects the Lie algebra. If we take two elements and we take their bracket and then apply the group action, that's the same as first applying the group action to each of the two elements and then applying the bracket. All right, and the second part of this proposition is that these maps that we saw before, this triangle of different manifestations of the Lie algebra, these maps are all G equivariant. So they're Lie algebra isomorphisms, as we saw, but they're G equivariant with respect to this adjoint action that we just saw. So in other words, the adjoint action, these three actions are all identified under these isomorphisms. Okay, so so this note, this is what I said before, that these actions are well defined because the lambdas and the rhos commute. Okay, so what's the idea behind this proposition? In the cases of the action on left invariant and right invariant vector fields, it's kind of easy to see the compatibility with the Lie bracket, because there the Lie bracket is the commutator of vector fields, which is just the composition of derivations in the opposite order. So we have the cancellation of the rho g's or lambda g's in the middle because we do the conjugation. So that's easy to check if you write it out. For the adjoint action on the tangent space at identity, we need a little bit of setup. So the first thing to observe is that we have the following commutative diagram. So this basically shows that the conjugation map is a group homomorphism. And that's easy to check. So if we take two elements and first multiply them and then conjugate the product by little g, that's the same as first conjugating each of those by little g and then taking the product. And that's because in the middle we get a cancellation. We have a g inverse times g and that goes away. So that's why this commutes. And because this commutes, we have a corresponding commutative diagram on the level of algebras. So if we just pull back along each of these maps, when we pull back along the multiplication map, we get the coproduct map. If we pull back along this conjugation map, well, we get some algebra homomorphism that's just denoted CG star, and we have this commutative diagram. So this is on the level of algebras. So in other words, this pullback is a co-algebra homomorphism. Okay, so how do we use this? Well, now let's so remember, we wanted to show that this adjoint action respects the Lie bracket. So the Lie bracket on the tangent space at the identity is given in terms of the associative algebra structure on the dual space of the affine algebra. So let's take two tangent vectors, two elements of the Lie algebra, xi and xi prime. And we want to compute what their product is in this associative algebra. So this product won't necessarily live in the Lie algebra, but it'll live in this bigger space. Which is the dual space of affine algebra. What we want to show is that this product in fact coincides with the following thing. So it coincides with what we would have gotten if we just took their product before applying the adjoint action, and then composed by and precomposed by CG star. So and in turn, this to verify this, we just write one big diagram, and then it becomes pretty obvious. So we have this commutative diagram. So the reason this left square commutes is that's coming from that we just argued a minute ago from the fact that conjugation is a group homomorphism. And what about this right square? Why does it commute? Well, it comes down just to the definition of the adjoint action. So on this side, so here in this top arrow, we're applying the image under the adjoint action of xi in the first factor, and the image under the adjoint action of g applied to xi prime in the second factor. But by definition, the adjoint action first precomposes by CG star, and then applies xi or xi prime, as the case may be. And so that's why this right diagram commutes. So it's just nothing more than the definition of the adjoint action. So maybe, yeah, you can stare at this for a while to convince yourself, but it's nothing too deep here. And so, okay, so because each of these two parts of the diagram commute, the whole diagram commutes. So now we make the following observation. So on the top, that's just the definition of this product, adjoint G applied to xi times adjoint G applied to xi prime. So that product is just this top composition. And so that's the same as going down and over. So at the end, we just end up at K. So if we go down and over, that's exactly precomposing the product of xi and xi prime with CG star, which is what we wanted to show. And once we have this, we're pretty much done, because now, yeah, so what do we do? So we wanted to show that we wanted to show that the action of G respects the bracket. So let's apply the action of G to two elements in the Lie algebra, xi and xi prime. That by definition is not by definition, we just showed that that's given by that each, so this is a commutator, and so it's the commutator of two things, and one of those things is this, and the other thing is this in the opposite order. We just showed that this is equal to this, and in the opposite order, we would get xi prime times xi precomposed with CG star. So I guess to be more clear, I should have included one more step in this equality, but you can write it out for yourself to convince yourself. And so now here we can factor out the CG star, and what we're left with is the commutator of xi and xi prime. And precomposition with CG star is exactly the adjoint action on this element, applied to this element. So we get that this is the adjoint action of G applied to the bracket of these two elements. All right, so that was kind of a mouthful, but it's just a lot of symbols. It's pretty straightforward once you convince yourself of this diagram commuting. And what about part two? So for part two, we need to show that all these maps are G equivariant. So I'll focus on showing that the map from left invariant vector fields to G is G equivariant. So this map is just evaluation at the identity. So you post-compose with the co-unit map. And so to see this, it's another diagram trick. So of course you don't need the diagrams, but I find it easier to understand this through diagrams. So that's why I wrote out these diagrams. So first of all, we have that this map this diagram commutes. So this is if we start at the identity, we include in G and then apply the right multiplication action at G inverse, then we end up at G. And similarly, if we include the identity here and then apply the left translation action, we end up at G. So this commutes. That's pretty much trivial. So as a result, we have this commutative diagram. So here we apply rho G, which is our G inverse star. And then we apply eta, the evaluation at the identity, the co-unit. And that commutes, so that composition is the same as first doing lambda G inverse, which is the pullback of LG, and then evaluate that identity. Okay, so this is just some diagram nonsense, but this is helpful because now if we have something in a left invariant vector field, then let's compute, so we want to show that this map that sends theta to eta composed theta is G equivariant. So let's first start with G dot theta. So G dot theta by definition is conjugating by rho G. And now now we drop the parentheses. So because rho G, so doing rho G and then doing eta is the same as doing LG inverse and then doing eta. So that's how we get this equality. And now we use the fact that theta is left invariant, so it commutes with LG inverse. And so we have it on the other side that explains this equality. And now what are lambda and rho? Those are pullbacks of some maps, so we write them in that way. But now you can observe that if we do RG and if we do, well, actually the order changes. So if we do LG and then RG, that's the same as conjugating by G, because we multiply on the right by G inverse, we multiply on the left by G. So that's just CG. So that explains this equality. And now precomposition with CG star is the adjoint action of G. So this, we get the final equality, and that's exactly what we wanted to show. And so that's the argument for left invariant vector fields. For right invariant vector fields, it's the same thing. If you want to show that the map from left invariant vector fields to right invariant vector fields given by conjugation by the antipode is G equivariant, you could do it by hand. It's not too bad, but it actually follows from the G equivariance of the other two maps because we already have this commutative diagram of isomorphisms. Yeah. All right. So that was the proof showing that these different realizations of the adjoint action are all the same thing. Okay. Any questions? All right. So if there are no questions, I'll move on then. So yeah, just one quick remark. So so when we were showing that the adjoint action respects the Lie bracket, we in fact showed that the adjoint action extends to a Lie algebra automorphism, in fact an algebra automorphism of the dual of the affine algebra of this whole big space. So that's just, I don't think we'll need this, but just thought I'd point it out. All right, so, okay, so what are some examples? Let's try to stay concrete. So we saw that the Lie algebra of GLN is n by n matrices with the bracket being just the commutator. And the adjoint action is just matrix conjugation, this should say matrix conjugation, but the formula is correct. So we can, anytime we have an invertible matrix and some other matrix, we can conjugate that other matrix by the invertible matrix. And to see this, it's, yeah, so this is just a computation using that isomorphism from before. So we can think of these as inside of well, yeah, we don't need to think about the affine algebra. We can just directly think about this isomorphism, and also we have the pullback by the conjugation of G, and so when you write it out, you see that this pullback map amounts to just conjugating by the matrix G. All right, and so for SLN, we have already that its Lie algebra is traceless matrices, and the adjoint action is again given by conjugation. So so here the only thing to point out is that trace is conjugation invariant. So if we conjugate a matrix by any invertible matrix, then we get the same trace. So in particular, the conjugation preserves this space of traceless matrices. So here we're actually, technically the adjoint action is only conjugation by SLN, but it's true even with GLN. Yeah, we get an action even with GLN that preserves the trace equals 0 condition. All right, and this, yeah, and the trace, and we didn't need xi to have trace 0. This equality is still true for any xi, but we only need it for the scope of this example, we technically only need it for trace equals 0. So something slightly different with the orthogonal group. So with the orthogonal group, we have, maybe I should have written SON here because it's the same as ON, and it's more conventional to write it as SON. But anyway, we have that the Lie algebra is these Q-symmetric matrices. The adjoint action is again matrix conjugation. Here, one thing to point out is that if it's important that we're conjugating by orthogonal matrices. So it's not true that this condition is preserved when conjugating by any matrix. We need to be conjugating by an orthogonal matrix for this to be for this condition to be preserved. Right. Okay. So that's the orthogonal group example. And one more thing. So if we have a commutative group, then this conjugation CG, that map is just identity map. So the adjoint action becomes trivial. It's the trivial representation. And the converse is also true if G is connected. So if the adjoint action is trivial, then the group must be commutative. Right. So, yeah. So I another kind of aside, something that probably we won't need in this class, but I thought I'd point it out anyway. So we discussed so far just adjoint action of G on its Lie algebra, but there's the co-adjoint action, which is the action of G on the dual of the Lie algebra, on the cotangent space. So this dual doesn't have a natural Lie algebra structure. And in many cases, it's isomorphic to the original Lie algebra, but there's no natural Lie algebra structure. But there's still this co-adjoint action given by the following formula. So basically, in order to G acts on a covector by sending it to the following covector, the covector that sends xi to the evaluation of the original covector at the translate under the adjoint action of G inverse of xi. So yeah, so we evaluate this, and what the dual of the Lie algebra has that the Lie algebra does not have is a symplectic structure, and the symplectic leaves are exactly these co-adjoint orbits for the G action. So yeah, so that's just an aside for those of you who are interested in symplectic geometry.
How is it just defined? I didn't understand the definition. It seems maybe I missed something, but you define the dual. Well, you define here, but you already took psi, right? G, and how do you, psi is what? Psi is the parameter to the functional?
Yeah, so xi is something in the Lie algebra. So this is the
Oh,
dual.
I
Yeah.
missed the star. I missed the star. Psi star. Okay,
Yeah.
thank you.
So this is a general thing. Anytime we have a representation of a group, there's a representation of a group on a vector space, and there's the same formula defines the representation of the group on the dual vector space. That's it basically. And this is defined so that this evaluation map from the dual vector space tensor the vector space to K is this map is G invariant. Okay, so yeah, so this is not super important, but I thought I'd mention it. Okay, so now we want to go back to thinking about the vector fields on G and a way to understand all the vector fields on G in terms of the left invariant ones or the right invariant ones. So first recall that we had isomorphisms of Lie algebras between the tangent space at identity and the left invariant vector fields and the right invariant vector fields. So the isomorphism I gave was in the other direction, but we have one in this direction, obviously. So this isomorphism sends xi, so xi in the Lie algebra, tangent space at identity, to a vector field, and the value of that vector field at little g in the group is the image of xi under the differential map of left translation by g. So this lives inside the tangent space of little g. And similarly for this map that goes to right invariant vector fields, and it's given by yeah, we use the right translation action here. Okay, so so let me state the proposition, and then we can take a short break. So if we have these two maps, then these extend to, so we just include both left invariant and right invariant vector fields inside of all vector fields on G. And so then we get these maps alpha L and alpha R. So these are maps of Lie algebras. And the claim is that these extend to isomorphisms of K brackets G modules from K bracket G tensor the Lie algebra to TG, to all vector fields in both cases. So we have these two isomorphisms between this. So, okay, so what is this K bracket G tensor, the Lie algebra? So this is a K brackets G module, and it's the action is just coming from the source factor. So this is a free K brackets G module. So we can pick a basis for the Lie algebra, and then we have a realization of this as a free K brackets G module. And the tangent, the vector fields at G, that's a Lie algebra, and that's a KG module, because those are just derivations from KG to itself. And so there's this isomorphism, there's two different isomorphisms between all vector fields and this this free module. So this is analogous to in differential geometry when you saw that a manifold is parallelizable when its vector bundle is trivializable. That's what's happening here. So the vector the tangent bundle of the group is parallelizable in two different ways, two different canonical ways. So that's what's in this proposition, and yeah, I think this is a good time for a break. So let's take a break and resume in about 5 minutes. All right. So okay, so we had this proposition. describing the space of all vector fields on G in terms of the left invariant ones or the right invariant ones. So, so let me give you the sketch of the proof. There'll be one thing that I won't prove, but I'll tell you how. I'll give you the idea of how it works. So let's do this for the inclusion of the left invariant vector fields. So if we want to write out a big formula for what this alpha map is doing, alpha tilde map is doing, well, it's doing the following. So if we have something in the tensor product, so an f in the affine algebra of G and xi in the Lie algebra. So now that this is supposed to be a tangent, a vector field, and so it's supposed to eat functions on G, so eat elements of the affine algebra and spit out new functions. So we have to say what happens when this function is eaten, and the output is evaluated at G. And so if you work it out, what happens is that we first have, so there's two pieces. So this f of G, that's just a scalar, times another scalar. And so that other scalar will be the left translation of xi applied to h. And yeah, actually, I don't think we need a G here. So that's just the left translation of xi. So that's a derivation from kg to the field via whose modular structure is given by evaluation at G, and that derivation is applied to h. So actually, we don't need this G here. Let me fix that. And so that's what the map is doing. And to see that it's injective, we just set the right-hand side equal to 0. So that must be 0 for all functions on the group and all elements in the group. And that happens if and only if, so it's a product of two things. So it's if and only if this f of G is equal to 0 for all elements of the group, or this part here is equal to 0 for all elements for all h and G. So if this f is 0 for all elements of G, then f itself is 0. So what we started out here is 0. That's fine. So what about this part? What if this part is 0 for all h? That means that this left translation of xi is 0 for all G. And that then we have to have the xi as 0 because this left translation is an isomorphism. Its differential is an isomorphism on vectors, on tangent spaces. So that shows injectivity. What about surjectivity? Well, here there's several ways to approach this. One way is the following. So take a basis for the Lie algebra. So this is the basis of the tangent space to the identity of the group. And now what we do is the following. So then if we take this basis and we apply the differential of left translation to the tangent space over any other point in the group, then we get a basis for that tangent space. So these left translates by the differential of these xi's. They form a basis for any of these tangent spaces. And so if we have some vector field, then we can think about the value of that vector field at any point in the group. So if we take a point in the group, little g, then that vector field will be some element of that tangent space, and we already have a basis for that tangent space, so we can write out that element in terms of this basis. So we get these coefficients. So for every I and for every G, we get a coefficient. And then the thing to show that I won't go into detail here is that this map from G to theta GI, so for each I, this map actually belongs to, is a linear map, is a polynomial map. that I think that's believable because we started out with this vector field that's a derivation from polynomial functions to polynomial functions. But I won't be super rigorous. I won't show that this actually belongs to KG. But in any case, if you believe that it belongs to KG, then we see it's pretty much automatic that function tensor xi, and if we take that function tensor xi and then take the sum over all the i's, then that will be something in that free k bracket g module that maps to theta. So that's the proof modulo showing this fact. And yeah, so there's another proof given in Springer, which has to do with the cotangent bundle. So looking at the Kähler differentials of the affine algebra of G, and showing that the Kähler differentials is a free module on the it's a tensor product of k brackets G with the cotangent space at the identity. So if you're not convinced by this proof, you can look at that one, and then from that it follows that the same is true for the tangent bundle. So for vector fields instead of one forms. All right. Any questions on this proposition and its proof? All right. So hopefully it makes some sense. Hopefully I haven't lost all of you. Yeah. So now we have these two isomorphisms. There's two ways to think about how an element in the Lie algebra defines a vector field. And so given an xi in the Lie algebra, we can compare these two vector fields that we get at any point in the group G. So what happens is the following. So this alpha L of xi and alpha R of xi, they differ at little g, so at the tangent space of little g, by the adjoint action of little g on xi. So that's a vague statement. So to be a bit more precise, we have the following commutative diagram. So if we have G, the Lie algebra, and then we do the adjoint action by an element in the group, and then we think of each of these as vector fields through the inclusion of left invariant and right invariant vector fields. So the source we think of as a left invariant, the target we think of as a right invariant vector field. And then we evaluate each of these vector fields at the little g, so the little g with which we acted. Then we get a commutative diagram. So that's the sort of the diagrammatic interpretation. So I guess I'm giving you several interpretations. This is kind of in words what's going on, the slogan. This is the diagrammatic interpretation. And you can also give an interpretation in terms of formulas. So in terms of formulas, what's going on here is that if we take if we act on xi by little g, by the adjoint action, and we think of this as a right invariant vector field, its value at little g will be what we would have gotten if we did something much simpler, which is just take xi, think of it as a left invariant vector field, and take the value at g. And so this is the formula that gives this equality, and that also shows that this diagram commutes. So it comes down to this. So I mentioned earlier that if you do right multiplication and left multiplication, then that's the same as conjugation, because the right multiplication has an inverse, and you use a variant of that here. So yeah, so the adjoint action, I mean, we have left invariant vector fields and right invariant vector fields, and I keep emphasizing that there's no canonical choice, and the adjoint action measures how they differ, how the difference between these two choices measures how non-canonical one choice is over the other. And if the group is commutative, then there's a canonical choice, which is reflected in the fact that the adjoint action is trivial for commutative groups. All right, so now I want to collect a bunch of facts. So these are a bunch of statements. Some of them, I guess, I've been using implicitly in the notes, and some of them there's maybe some more detail given in Springer about them, but I just wanted to make a record of them. So first of all, the dimension of the Lie algebra is equal to the dimension of the group. That's because the group is smooth, and the Lie algebra is the tangent space at the identity, so it has dimension equal to the dimension of the group. So that's the first fact. Second fact, if we have a closed subgroup of a linear algebraic group, so here G is always a linear algebraic group, then the tangent space, the Lie algebra of the subgroup is a Lie subalgebra of the Lie algebra of the whole group. The idea behind this, so I guess I won't give a complete proof, but it's not too hard. And the idea is the following. So if H is a closed subgroup, that means H is, the affine algebra of H is affine algebra of G mod some ideal. And the tangent space at the identity of H will be all the derivations that vanish on I. And yeah, and one needs to argue that this is in fact a Lie subalgebra, but it's not too hard to show. You can think about what happens on you can think either in terms of vector fields, invariant vector fields, or you can think of what happens with the dual space, dual of the affine algebras. Right. Okay. So that's fact 2. Fact 3a is the following. So if we have a morphism of linear algebraic groups, then in particular, the morphism takes the identity to the identity. And so we have the differential of this morphism that goes from the tangent space of the identity of G to the tangent space at the identity of H. And this map that we get is a Lie algebra holomorphism. So this is in fact pretty nice to show. So the way you show it is, so we have phi that goes from G to H, so that's a morphism of linear algebraic groups. So its pullback map will be a morphism of coalgebras, since it commutes with the multiplication maps. And so then the double dual map, so this phi star star that goes from the dual of the affine algebra of G to the dual of the affine algebra of H will be a map of algebras. And then you can just check that actually the differential at the identity of phi is just this double dual restricted to the tangent space at the identity of G. Yeah, so that's what's going on there. And we already know that this phi star star is a map of algebras. So then it's, if we have a Lie subalgebra on this side, then yeah, so it respects the Lie bracket. So if we have a Lie subalgebra here, then the map, its image will be, if we know that the image lands in a Lie subalgebra, then the bracket will be respected. Okay, so that's fact 3a. Fact 3b is a special case of this. So if we have a representation of G's, then that's in particular a homomorphism of linear algebraic groups from G to GLV for some vector space V. And so its differential, as we just argued, will be a map of Lie algebras from the Lie algebra of G to the Lie algebra of GLV. The Lie algebra of GLV is endomorphisms with the commutator. And what we get is a representation of the Lie algebra. So in other words, this gives us a procedure to produce representations of the Lie algebra from representations of the group. And so maybe we'll discuss this later in the class. I'm not sure if we'll have time, but If G is simply connected, then we get an equivalence of categories between representations of G and locally finite representations of the Lie algebra. So we already talked about the notion of a locally finite endomorphism, and locally finite representations are those for which the Lie algebra acts by locally finite endomorphisms.
I have a question here. Like,
Sure.
okay, if G is over some like connected field C or R, then simply connected here would really like make sense. But if in case we have some like totally disconnected topology on G, so this would be the definition of simply connected, right? Like some like the other way around.
I think you can still define a fundamental group
Right.
in those cases,
so
and then you could just say it's simply connected if it's.
okay, I know this as a definition of simply connected.
Oh, okay.
Somehow.
I guess that's
maybe,
also possible.
Maybe I'm.
Yeah.
I have a question about what you said. Why this is a map of coalgebras? Isn't this a map of Hopf-algebras?
It is a map of. It is indeed a map of Hopf algebras, but we only need the fact that it's so any map of Hopf algebras is in particular a map of coalgebras.
In what sense it's coalgebra? Why it's not a map of algebras?
It is a map of algebras, but we only need the fact that it's a map of coalgebras. So yeah, so this indeed is, so what's a map of Hopf algebras? So what's a Hopf algebra? It's an algebra and that has a compatible coalgebra structure and an antipode. Or equivalently, it's a coalgebra with a compatible algebra structure and an antipode. And so a homomorphism of Hopf algebra is something that's a homomorphism of algebras and a homomorphism of coalgebras. And so in particular, it's a homomorphism of coalgebras. But maybe you're asking why I said coalgebra and not Hopf algebra. That's because when you take this dual map here, we get an algebra structure, but we don't get a coalgebra structure. So if we had a map of algebras and we take the dual, then we don't get a map of coalgebras in general in infinite dimensions. In finite dimensions, it's fine, but in infinite dimensions, doesn't work that way. So this double dual is not a map of coalgebras in any sense. Does that help a little bit? I know it's confusing.
Yes.
Yeah. Okay. Right. So, okay, we have this fact. So there are more representation in the simply connected case. At least there are more representations of the Lie algebra, but particular specific ones. There's also sometimes called integrable representations are coming from the group itself. Okay, but that's an aside. Okay, fact 4. If we have two groups, G and H, then their product is again a group. We have the direct product of groups. And the Lie algebra of this product of groups is the direct sum of the Lie algebras. And this is coming from this general fact that the tangent space at a point in the product is the direct sum of the tangent spaces. So I think this was an exercise in the section on derivations. I'm not sure if I assigned it or not, but anyway, you can look back to that section on derivations and convince yourself of this fact. And so this gives us this isomorphism as vector spaces, but there's the question of what's the bracket on this side? What's the bracket of a direct sum of Lie algebras? Well, we can just do things coordinate-wise. So A comma B bracketed with B, C comma D is the bracket of A and C comma the bracket of B and D. So it works out. Right. So related to this, so let's think about the multiplication and the inverse map. So these are two maps that we always have for a group. what do they do on the level of Lie algebras? So if we think about the differential at the identity here, this would go from Lie algebra, direct sum Lie algebra to Lie algebra. And what is that map? Well, it turns out to be just the sum of the two Lie algebra vectors. What about on the inverse map? So the inverse map takes the identity to the identity. So it gives us a linear endomorphism of the tangent space at the identity. So a linear endomorphism of the Lie algebra. Which linear endomorphism is this? It's just multiplication by -1. So yeah, so I won't go through the proofs, but it amounts just to tracing. If you understand how this isomorphism works for any varieties, in particular for the group, then you can just trace through what happens, and you get these identities. So that's another fact. So I also want to mention universal enveloping algebras, but maybe are there any questions about these facts before I start this new topic? Yeah, you can look at Springer for more details if some of these things are confusing. All right, so let me introduce universal enveloping algebra. So as far as I could see, Springer does not talk about them, and I'll try to kind of be brief and just give an overview, because I think it's good for you to be aware of these things. So first let's start with the tensor algebra of a vector space. So if we have any vector space over a field, then we can produce this algebra. It's a non-commutative algebra. It's called the tensor algebra of V. So the definition is the following. So it's K, which we can think of, it's K, the ground field, direct sum V, the second tensor power V, direct sum the third tensor power V, and so on. So it's a graded algebra where the ith graded piece is just the ith tensor power of V. And the multiplication on this algebra is concatenation of vectors. So let's say we have something in the ith tensor power. That's a tensor product of some elements in V. So V1 through VI are just some elements in the vector space. And if we want to multiply that with something in the jth tensor power, then we have something that looks like this. So this is the definition for simple tensors. It extends in the obvious way to general tensors. So we have W1 through Wj. So these are each W is an element in V, but this tensor product of these W's lives in this tensor power of V, of capital V. And this product is by definition we produce this new big tensor product inside the I plus jth tensor power of capital V. So it's just concatenation. So this is a free construction. This is a free algebra on V. So if we pick a basis for V, then we can kind of write it more explicitly. We can write the tensor algebra more explicitly as the free algebra, free non-commutative algebra on these elements. And this dot here is to indicate that it's a graded algebra. Okay, so that's a tensor algebra. So we also have two other algebras, which are the symmetric algebra and the exterior algebra of the vector space V. So the symmetric algebra is, and so both of them are quotients of the tensor algebra. And we take quotients by some ideals. So for the symmetric algebra, we take the quotient by the ideal generated by V tensor W minus W tensor V for any two elements V and W in the vector space. So this V tensor W minus W tensor V, that's a non-simple tensor in general inside the second graded piece, inside the second tensor power of V. But we take the ideal inside the algebra generated by this thing. So in particular, that'll be a homogeneous ideal. It's generated by something that's homogeneous of degree 2. And so the quotient will have will also be graded, and yeah, this dot indicates the grading. For the exterior power, and this quotient will be commutative. So this basically imposes the commutativity condition, and this quotient will be commutative. But for the exterior power, we do something similar, except we take plus, and then we'll have this anti-commutativity. When things commute, we get a minus sign popping out. So they're both graded algebras, and we have the images. So we could take the dth tensor power of capital V and look at its image in either the symmetric algebra or the exterior algebra. That'll be a graded piece of each of these algebras. Sim dV and exterior dV are the images. So these will be, if V is finite dimensional, these will be finite dimensionals. You can write down what the dimensions are as certain choose functions in terms of the dimension of V and D.
T tensor D. What do you mean? All the power until the D, or only D?
Oh, sorry. This should be a V. Sorry about that. Is that what you were asking?
Both. Yes. Thank you.
Yeah, we take D, exactly D tensors. So this is capital V. I don't know if I can increase the size. Yeah, anyway. Yeah, we take...
You need to mark it. You need to mark the V. Okay.
Yeah, I'll do it later. But this is a capital V. I need to take this. So like something in I guess I used I here, but if we take just D, different vectors, well, not necessarily different, just any D vectors in V, then we can form this tensor product. Is that what you're asking? I'm not sure what the question is.
Yes, okay. Yes, just how you multiply how the multiplication goes. Oh, it's the image. Okay.
Yeah, so the multiplication in the symmetric algebra is commutative. So we can if we fix a basis, then we can just order everything in our basis in the symmetric algebra. And like, so yeah, so we'll have some number of V1s, then some number of V2s, and some number of V3s, and so on with some coefficients that will give us a basis. For the exterior algebra, we also get something similar, except we have to be careful because V tensor V goes to 0 inside the exterior algebra, and V tensor W goes to minus W tensor V in the exterior algebra. So sometimes we get zeros, and sometimes we get these minus signs coming up. And in particular, if we take D to be more than the dimension of V, then the exterior power is just 0. The Dth exterior power is 0. Right. Are people okay with this so far? So, okay, so as I said, this sim is a commutative algebra. And it's, in fact, if V is finite dimensional, then it's an affine algebra. There's an associated affine variety, and it's the most natural thing is to think of that affine variety as the dual space of V. Because I mean, you think of these as functions, you think of elements in V as functions on V star. And so the symmetric algebra of V will be actually the affine algebra of V star, of the dual space. And it's more concretely, it's just a polynomial algebra. So the tensor algebra is the free non-commutative algebra on some elements, and the symmetric algebra is the free commutative algebra on some elements. So in other words, the polynomial algebra on some elements. Right. Okay, so that's kind of just some things we needed to point out. What we really want to think about is the universal enveloping algebra of a Lie algebra. So let's take frac G, math frac G, to be a Lie algebra. Then its universal enveloping algebra is also a quotient of the tensor algebra of G, but it's a quotient by a different sort of ideal. So it's, I guess to be precise, I should have said that this is the ideal generated by these expressions for all xi and xi prime in Lie algebra.
Why is this ideal different than the exterior algebra ideal?
Yeah, so for one thing, it's not homogeneous. So this, what we have here on this side is something, it's a two tensor, something that lives in the second tensor power of G, but the bracket of two elements in G just lives in G itself. So this is something in degree 2 related to something in degree 1. So the universal enveloping algebra won't be graded in general. It'll be graded only if the Lie algebra is commutative. Does that answer your question? Okay. So so when working with this, we often will drop the tensor sign. So I may do that later. And yeah, so as I said, if G is commutative, then this bracket is 0. So then we just get the same ideal we had in the symmetric algebra. So then the universal enveloping algebra is just the symmetric algebra on the Lie algebra, thought of as a vector space. In fact, yeah, then the Lie then it doesn't have, if the Lie algebra is commutative, it doesn't have any extra structure. It's just a vector space. And as I pointed out, it's not graded in general. There is a filtration. So if you guys are familiar with filtrations, there is a filtration on G. And okay, so then what's an example? The universal enveloping algebra of SL2. So this is a K here. I think I wrote C out of habit, but it's a K here. So it's a quotient of the free algebra on 3 generators, E, F, and H, the same guys we saw before. And these are the relations. So before we had that, there was a commutator going on here. Now we think of, it's also a commutator, but we think of this as inside of a bigger sort of algebra. So we have inside this free algebra, we have this, we have these elements E, F, and H, and we can think about their products, and we can, inside the free algebra, we can take arbitrary lengths of products and it won't be commutative. We can't switch things around. But we quotient that free algebra by these relations. And that gives us the universal enveloping algebra of SL2. And we can, one thing, so if you want an exercise or something, you can show that this element, EF plus FE plus 1/2 H squared, is central inside the universal enveloping algebra. So you can use these relations to show that this is central. You just need to show that it commutes with each of the generators. Right.
What did you do especially? Those relation we already have. So what did you quotient by? This you already have those relation before in okay. Understand me?
Yeah, I understand.
You already have it. So where
we did, not quite, because what we did was we took the free algebra on EF and H. There's no relations in the free algebra. And then we imposed these relations in that free algebra. So the reason these are the relations we imposed is coming from the bracket on SL2. But to start with, we didn't have, I'm not sure if I understand the question actually.
So this seems like SL2. Why this you call this the universal one?
Because
What
this is an algebra, it's not a Lie algebra anymore. It's a big, I mean, it's not, we can always do the forgetful functor, but this is an honest to God algebra. So Lie algebra is not an algebra in general, but now here we have something that is an algebra that encodes the Lie algebra structure.
It's not finite dimensional, for example, right?
Yeah, it's not finite dimensional.
And SL2 will be.
Mm-hmm.
Okay,
Does
thank you.
help, Tal?
Yes, I think so. Because what Chivi also said. Yes, it's
Yeah,
not
so
fitting something.
you can also think about the abelian case or the commutative case. So if we had a commutative Lie algebra, so take your favorite commutative Lie algebra and compute what its universal enveloping algebra is, and you'll see that it's just a polynomial algebra. So it's an algebra, like it's all polynomials. But the commutative Lie algebra you started with is going to be something finite dimensional. So that's a way to understand this a bit better. Okay. So let me collect some facts. So these facts are going to be a bit abstract, I guess. Yeah, I think it's good to be aware of them. We may not need them so much in what comes later in the following few weeks of the class. But let me just point them out. So we already saw that there's this forgetful functor from associative algebras to Lie algebras. And this universal enveloping algebra construction is a left adjoint to that forgetful functor. So yeah, so the forgetful functor gives us a Lie algebra for any associative algebra. This gives us an associative algebra for any Lie algebra. And the forgetful functor doesn't change the underlying vector space, but this universal enveloping algebra functor is a free functor, and it gives us something huge in general. And so what we have is that if we think of representations of our Lie algebra, so those are Lie algebra homomorphisms from G to GLV, then those will be the same as associative algebra homomorphisms from the universal enveloping algebra to the endomorphism algebra of that same vector space V. So in other words, representations of the Lie algebra are the same as representations of this universal enveloping algebra. And sometimes it's easier to think of things as representations of a certain algebra as opposed to a Lie algebra. There's maybe more techniques that we can use. There's more structure. But sometimes it's nice to have something that's just finite dimensional, so we can go back and forth. Okay, and also as a vector space, so it's as a vector space, this universal enveloping algebra is isomorphic to the symmetric algebra on the underlying vector space of the Lie algebra. So this is only as vector spaces, and it's only true that they're isomorphic as algebras if G is commutative. Let me point out something for those of you who know what filtrations are, that filtration on the universal enveloping algebra that we had before, we can take the associated graded with respect to that filtration, and then we recover exactly the symmetric algebra. But that's not important. And one thing that we have is we always have the Lie algebra sitting inside the universal enveloping algebra. And we can always recover the Lie algebra from the universal enveloping algebra by looking at the commutators. So, yeah. And finally, because this is, we started today talking about the adjoint representation. So we had the adjoint representation of G on the Lie algebra. And this extends to an action on the universal enveloping algebra by algebra automorphism. So really what happens is we extend it to the tensor algebra, and then we show that that ideal is stable under the G action. And so we get an action on the universal enveloping algebra. And here I want to point out that whenever we act on a tensor product, we act factor-wise with the little g. So g acting on this tensor product is a tensor product of g acting on each of the factors. And it's very, yeah, so in representation theory, it's a very important thing to look at the centers of non-commutative algebras, and in particular, think about what the center of the universal enveloping algebra is. And the center will be the things that are invariant under the adjoint action. And maybe we'll get to a theorem later on, Chevalier restriction theorem, that describes this center in a different way, in a somewhat more manageable way. So yeah, so that was a lot of things. I hope I didn't overwhelm anybody. But yeah, so we still have a few minutes, so maybe I'll end the class now and I'll stick around for a few minutes in case anybody has questions.